I finally built a small Strix Halo cluster to run large language models by linking my framework desktop with the HP Mini workstation that you might have seen in some of my previous videos. Now, together, they give me a theoretical total of 256 gigabytes of unified memory, which is more than enough to host large models at high quality quantizations like the great Unsloth dynamic quants. Here you can see the new MiniMax-M2, a 230 billion parameter model in Q6K XL quantization, running at around 17 tokens per second, using around 200 gigabytes of memory across the two Strix Halo boxes. And this is GLM 4.6, a 355 billion parameter model in Q4 XL quantization, doing about 7 to 8 tokens per second, which is better performance than I honestly was expecting from this hardware setup. Now, the software stack I'm using is Llama.cpp with its RPC module, which allows Llama.cpp to use compute resources across different nodes, effectively turning multiple machines into a single logical inference system. In the rest of this video, I'll show you exactly how I set this up, and I was surprised myself by how easy this turned out to be. Alright, so let's start with the setup of the two boxes. So this is let's start from the framework desktop, which I'm going to use as the, I'd say, master host in this mini cluster. So this has a built-in Ethernet card, this one over here, and we can take a look at the performance of this one. It's a 5 gigabit card, and that's what you want because latency and speed are really important here. This is going to be your bottleneck for this particular setup. And I configured this, as you can see, with a static IP address 10.0.0.2. Now I plugged a Ethernet cable, a Cat6 high performance Ethernet cable into this Ethernet port, and I plugged the other end directly into the HP Mini. Now I didn't use the built-in Ethernet card there, and this is because if you look at that built-in Ethernet card that my HP Mini came up with, this is not the fastest that you can get. So instead I got myself a USB dongle with the faster Ethernet adapter. So you can see that I have essentially a 5 gigabit card here as well. So these are connected together, and the IP address of this one is .1. So that's what I did for my network setup. I did try to increase the MTU, maximum transfer unit, to 9000. I honestly didn't see a considerable performance improvement during inference, so you can keep the default value here. But that's all I did for the setup from the hardware point of view and the networking point of view. So then, how do I run this? On the HP Mini, which is going to be my slave, I enter one of my Llama.cpp toolboxes. The one to use is this one over here, the 7 ROCm MA, because this is the only one in which right now I have built the RPC support. And then I can simply, once I'm in here, I should have it in my history. There it is. You simply run the Llama.cpp RPC server. You bind it on your all the network interfaces on this port. And then it's very important to run it with the -c parameter for cache. And so this is now listening on that port. There is a cache in which it is going to store all of the layers which are going to be offloaded by Llama-CPP to this particular node. So the second time you try to run a model, it's gonna run faster. Now, the other thing which is important, you need to open this port in your firewall. Here, as you know, I use Fedora just because I find it works really well with toolboxes and with inference, but just ask ChatGPT how to open a port in the firewall of whatever you're using. But that's really all the setup you need. Now let's go on the main host, and again I'm gonna enter the same toolbox, which is this one over here. So I am on the framework desktop inside the toolbox, and I have some of my models downloaded to this folder. Now I got MiniMax-M2 and I got it in this Q6K-XL quantization. This is a very, very good quantization that we can go and check here. Actually, let me just show you where you can get the model. So typically I filter for GGUF, which is the format we need, and you can see here the Unsloth quantizations come up. Now if you look at this table, this kind of gives you an idea of how much we can fit in memory, and for us this Q6K-XL quantization just below 200 gigabytes is perfect. And again, you can see this is a fairly large model, 230 billion parameters with 10 billion active parameters. This is a mixture of expert model, and this is really what I recommend on Strix Halo boxes. Like if you have a dense model that is not going to perform well, just the hardware is not built for those types of models. But for this one, it's going to work fantastically. So then what I did, I know that there are different ways of downloading the models or the model weights, but what I do, I go into the folder and I download the individual files. I think in one of my previous videos, I show you how to do this, but maybe I can quickly show you here. You can see me running this command over here, which basically simply uses Hugging Face CLI to download from that repository under that folder the different parts of the model. You have to have all of the parts, and there are 4 parts to this model. So let me just re-enter the toolbox and go into that folder. MiniMax. So you can see the weights are here, and now simply I can run Llama server. As usual, you do require, because we're using ROCm, there is a problem with Llama-CPP if you do not specify the no memory map feature. I told you this in the first video that I did on Strix Halo. I enable flash attention. There is really no reason not to enable it. This is going to make inference faster and consume less memory. And then I pass the first shard of the MiniMax model, and this is the new parameter that you need. You basically need to put --RPC, the IP address of the server you are running the RPC server on, and the port number, and then as usual the layers that you want to offload to the GPU, in this case all of them. Now when you run this, what's going to happen is that memory is going to be allocated locally first, and then on the remote server. And the way the Llama Llama.cpp RPC works is that it splits it into half, or like if you add more, it would distribute the model weights like in equal proportions. So if I go on my framework desktop and I look at the memory, that's what's being allocated, and the weights are currently being copied. And if I go on the HP Mini, likewise, memory has been allocated there as well. So now the weights are being copied. So this will take some time. The first time you do this, it is going to take around 6 minutes in total, because after loading the weights locally, which is fairly fast, it's going to need to transfer around 100 gigabytes of layers to the HP Mini, and so that's going to take some time. The second time you do this is going to be slightly faster if you used the -c parameter, which basically creates a cache. It is still going to take around 3 minutes, because it is still, I think, checking whether it's got the layers cached, but at least because the layers will be there, it will not have to transfer them. Actually, let me just very quickly show you what's in that cache folder. These are all of the layers that have been kind of cached here, and because we can see the disk usage of this folder, 284 gigabytes, because these are actually weights for, or partial layers for 3 models that I have already run on this machine. So again, this is going to take a while. Again, 3 minutes, that's what I am expecting here. So I'll let it run, and I'll come back when this is loaded. All right, this took actually less than 3 minutes. The Llama-CPP server is now running on port 8080, and as I showed you in the other video, I SSH into these and I forward that port locally, so I can actually go into my browser and just visit that, and this is now MiniMax loaded, and I can start using it. For example, I can say write me a small heap kernel to multiply two matrices, and you can see that this is now running, and there it is. So it's actually fairly fast. I think we should be seeing the stats. I just don't remember how to make it show tokens per second. Okay, that's probably better. So you can see this is around 17 tokens per second. Now this is a reasoning model, so it is still reasoning. Oh, you can see the context. By default, the context is going to be 4K. Actually, we should probably rerun these with a larger context window. So let me just kill these. And if you want it with a larger context window, let's say we're going to do 60,000 tokens. Obviously, this is going to take more memory. And again, it's going to take around 3 minutes again to reload these models in memory across the network. So I'm just gonna let it do this, and I'll come back in a second. Okay, so this is now up and running, and we can go back to the web interface and see now the context size is much larger, and I do expect that also the memory utilization on the boxes will be larger. Like for some reason, Llama-CPP chooses to allocate a little bit more memory on the other host. You can control the split of memory if you want. There is a command line parameter that you can specify when you run Llama server, but I'm not going to do that because honestly this seems to work fairly well. But again, if you go back in here, I'm just going to ask the same thing that I asked again. Write a small heap kernel to multiply two matrices. And by the way, heap is the programming language that AMD has for its like ROCm stack, similar to CUDA. And again, this is a reasoning model, so you see all the reasoning around 17 to 18 tokens per second. It thinks a lot. This is a thinking model. Now, actually, one of the things that you can do, you want to look at the documentation of the model, but you can control how much they think. For this particular model, I seem to remember I can just say no think to kind of in the system message, and maybe that is going to stop the thinking, or at least make it think a little bit less. Let me see. No, it still does that. Let me try. You know, I remember reading somewhere that you could just cause the model not to think, but obviously this one just wants to think a lot. Oh, okay, so it's thinking much less, and this is the output, which is honestly not bad. Again, almost 18 tokens per second. You can fit a very large context in here. Obviously, as the context becomes larger, the performance will decrease, as you can see. But anyway, you get a very high quality model here. So this is really good. The other model that I'm going to show you is GLM 4.6. Now, this is a much bigger model, which means that we need a smaller quantization. And as usual, if you go here on Hugging Face and you select models, and then you filter for GGUF, and then we find, we said, what do we want? We said we want GLM 4.6. There it is, again, the Unsloth quants, and just by looking at the table, we know that we could fit a 4-bit quant easily. In theory, you could also fit a 5-bit quantization. This might just about work, but remember, you need to leave some memory for the operating system, so I wouldn't go for that one, and instead I went for this one, which is 204 gigabytes, and in fact, that's what we're going to run now. I think I saved these in my own directory. Now that's GLM Air. So you actually probably here as well. Yeah, that's where it is. There are 5 shards here instead of 4, but the command to run these is exactly the same. I'm just going to run it with a smaller context, but it shouldn't matter too much. And obviously I will pass it the first GGUF file. And again, this is going to do exactly the same as before. It's going to allocate memory on both nodes. Sorry, the AMD GPU top command gets screwed up, but you can see the it's allocating already more memory, and that's the same here. And now it will start loading the weights first inside this memory that's allocated here, and then over the network it's gonna send the weights to the HP Mini. Again, the weights are already cached, so it's gonna take a little bit less time for this model to come up, and I'll be back when this is loaded. Okay, this finished loading. Again, it took around 3 minutes. You can see all the memory that's been allocated here. So here we have over 200 gigabytes of RAM allocated. We just refresh this, and now we know that we've got GLM Air, and we can say maybe the same. What again I did here, oh, by the way, that's why it wasn't working before, because I had two things instead of no thing. And again, I don't remember which model this works, but let's try write a small heap kernel to multiply two matrices. And I keep having a lot of typos, and it is still reasoning. Now, obviously, you can see this is around 8 tokens per second, a little bit more than that. Still fairly good. Again, there is nothing wrong with the thinking, but just in case, I think just if you are interested and you don't want the thinking, I think this is the model that if you just add these at the end, it might not think. Okay, that's it. So we just get the response out of this. And again, performance is okay. This is extremely usable, and it's gonna have a decent approximation and quality. However, this is, as I said, one of the Unsloth Q4 dynamic quants. This is better than a regular Q4 quantization, because they keep some of the, I think, attention layers at full precision, or some of the critical parts of the model at full precision, which improves considerably the performance. But there it is. Not the fastest, but definitely usable. Now, I would still prefer, honestly, something like MiniMax. Basically, I think the sweet spot for this dual Strix Halo setup is a model in Q6 quantization of around 200 gigabytes, which means you need a model with 230 billion parameters. These are going to run very well, and again, with this Unsloth dynamic quantization, the approximation of the performance is going to be the quality of the output is still going to be very close to what you would get if you were running the full model. So I also run Llama-Bench on both MiniMax-M2 and GLM 4.6. So we have some tangible data. You can see the results here. Obviously, for MiniMax-M2, the performance is fairly good and usable. 166 tokens per second for prompt processing is not bad at all, and 18 tokens per second is actually a fairly decent token generation speed. Now, for GLM Air 4.6, I think this is again where you're really stretching what Strix Halo and what the setup that we have with like this Ethernet connection can really do here. 33 tokens per second is not great as prompt processing, and 8 tokens per second is just about usable, but this will degrade as the context length becomes larger. So to sum up, I think the sweet spot here where this is usable and might make sense from a financial point of view is that you can acquire 2 of these Strix Halo boxes and link them together very easily to run models of around 230 billion parameters in Q6 KXL quantization, which is those that quantization, dynamic quantization by Unsloth, because it really preserves as much as possible the quality of the output. And again, you can fit that into 2 Strix Halo boxes with a fairly large context. Now, I have no idea how this setup might perform if you add 1 or 2 more hosts. Now, I know Alex has 4 framework desktop motherboards, and is going to try to replicate this setup with Llama-cpp RPC, which simply means connecting these boxes, and instead of just passing one host, you are gonna pass all of the other hosts. But I expect this will not perform as well. It will allow you to run DeepSeek, for example, or Kimi at a decent quantization. Actually, I would love to see how that setup can run the Kimi model. Let me just find, for example, this one over here. No, actually, Kimi is too big and it will not fit. Even like a Q2 quantization will not fit. This is Donato from the future. While I was editing this video, I realized I got confused. Obviously, you can fit Kimi thinking. You can probably fit the 3-bit quant into 4 of these, because obviously you have around 120 gigabytes times 4, so the 3-bit quant should actually fit into that model. And honestly, the same goes for models like DeepSeek. Like if we go and check this out, DeepSeek R1, you can probably fit a Q4 quant or even a Q5 quant. But again, I doubt that any of these will perform very well because of the network latency and all of the parameters that need to be activated across all of the different Strix Halo boxes. But I'm actually really looking forward to see what Alex manages to do with this.